smaller than the width of a human hair divided by 50,000 times.
But before anything gets built, you have to enter the clean room. This is where the magic happens, and it's the most hostile environment on Earth to dust.
One particle, one microscopic speck of dust. That's all it takes to destroy an entire $10 million wafer batch. Contaminate, ruin.
The air is filtered 10,000 times per minute. Not 1,000, not 5,000, 10,000. They put on sterile suits, face shields, booties, gloves, multiple layers. They look like astronauts because they basically are. They're about to work in an environment cleaner than a hospital surgical suite. Actually, cleaner than anywhere on Earth. It all starts with silicon. Pure silicon, 99.99% pure. That's 11 nines. 11. It comes in ingots, cylindrical blocks. Perfect, flawless. These ingots are sliced into wafers, thin discs, paper thin, but not fragile. A single wafer is about 12 inches in diameter. But here's the remarkable part. A single wafer will produce hundreds of chips, hundreds of thousands of transistors per square millimeter. The wafer gets loaded into the first machine, the spin coater. It spins at thousands of RPMs, coating the wafer with photoresist, a light-sensitive chemical. This coating is only microns thick, invisible to the naked eye. Yet this layer determines where transistors go, where circuits form, and where electricity flows. Now comes the most expensive part of chip manufacturing, lithography. A single lithography machine costs $180 million. Let me say that again, $180 million for one machine. This machine does something that sounds impossible. It projects an image onto the wafer using extreme ultraviolet light. This light is being focused to create patterns smaller than the width of a virus, and it's accurate to within 10 nanometers. The wafer gets exposed to this light. The photoresist reacts. Chemical bonds break. The pattern gets imprinted. The wafer gets dipped into a developer, a chemical bath that removes the exposed photoresist. What's left behind? A microscopic pattern. Billions of them. Across the entire wafer. These patterns are the blueprint for transistors. But transistors aren't built yet. They're just outlines.
Now the real manufacturing starts.
A modern chip isn't flat, it's three-dimensional. It has layers, dozens of them, sometimes 100+ layers stacked on top of each other. Each layer is a few nanometers thick. Each layer needs to be deposited, patterned, etched, and connected. So the process repeats, over and over, deposition. The machine maintains a vacuum, near perfect vacuum, because any stray molecules floating around will disrupt the process. The machine vaporizes materials, silicon dioxide, silicon nitrides, and deposits them as thin films onto the wafer. The thickness? Nanometers. Actual nanometers. It's like laser cutting, but with atomic precision. The wafer is bathed in plasma. Reactive ions bombard the surface. Unwanted material vaporizes.
What's left? Microscopic trenches, channels, pathways for electricity.
After each step, the wafer gets cleaned intensely, because even a few atoms left behind can cause circuit failure. Repeat, layer, pattern, etch, clean, repeat, hundreds of times. A modern chip might go through 600+ manufacturing steps. Let's talk about the equipment, because these aren't machines, they're marvels. The lithography machine, $180 million, size of a house, requires its own facility with vibration isolation. Vibrations smaller than an atomic nucleus will throw off the precision, so it sits on active isolation systems. Hydraulic suspensions that compensate for vibrations in real time.
The etch machine, $40–60 million, creates plasma environments reaching 10,000 to compensate for vibrations in real time.
Uses 50 different computer-controlled parameters. Adjust one by 0.1% and you ruin a batch.
The deposition machine, $30–40 million, operates in near-perfect vacuum, creates films layer by layer, atom by atom. The inspection machine, $20–30 million, uses AI and quantum imaging to scan wafers for defects, detects particles smaller than the width of a bacteria.
A single fab might have 3,000+ machines. Total equipment cost? Billions. And that's not counting the buildings, the clean room infrastructure, the utilities, the cooling systems. A fab uses as much electricity as a small city. Water storage tanks and cooling systems, visualizing the immense scale of 10 million gallons. This infrastructure powers massive utility requirements. Here's the brutal reality of chip manufacturing. Not every chip works. It's called yield, the percentage of working chips per wafer. A yield of 70% is considered excellent. That means 30% of the wafers, worth millions of dollars, are scrap. Because the tolerances are so tight that even microscopic variations cause failure. A single dust particle. So factories obsess over yield. Engineers analyze every failure, every defect, every anomaly. They use AI and they adjust machines by fractions of a degree. Because in a $20 billion factory, every percentage point of yield improvement is worth hundreds of millions of dollars. Before a single chip leaves the fab, it gets tested. Electrical testing. Machines apply power and check for shorts, opens, and performance. Functional testing. Computers run code to verify the chip works as designed. Test code visible on monitor screens. Chips being functionally validated. X-ray inspection. Deep inside the chip, layers are scanned for defects invisible to the eye. Temperature cycling. Chips are exposed to extreme heat and cold to ensure they don't fail under stress. A defect gets caught, the entire batch gets quarantined and analyzed. Sometimes the entire production line gets shut down to investigate.
Because a single bad chip in a customer's device can destroy a company's reputation.
After weeks of processing, after 600 plus manufacturing steps, after billions of transistors, the wafer finally gets cut. A precision blade, thinner than a human hair, cuts the wafer into individual chips.
Mounted onto circuit boards, connected with gold wire thinner than a human hair.
Then they're sealed inside plastic packages. These packages get shipped across the world. They end up in smartphones, data centers, AI systems, gaming consoles, televisions, everything. Let this sink in. A single fab produces 1 million wafers per year. Each wafer produces 300 to 500 million chips per year. And each chip contains billions of transistors, all manufactured at tolerances of 5 nanometers, or 3 nanometers, or smaller. The smallest feature on a cutting-edge chip, 0.03 micrometers. That's invisible, smaller than wavelengths of light.
And it's manufactured millions of times per day with precision measured in atoms. This is the most complex manufacturing process ever created. It requires
300,000 plus workers globally, $20 billion per factory, 25 plus years of research, thousands of patents,
hundreds of advanced degrees, and years of experience.
A single $20 billion fab manufactures more computing power in 1 year than existed in the entire world 30 years ago.
It's a temple to human engineering, a monument to precision, a factory where we build the future.
The next time you hold a smartphone, remember, inside that chip are billions equipment.